Hey everyone, I'm Miss Hu, your physics teacher. In this video, I'm going to go through the gold foil experiment in terms of the history of development of the atomic model, what the gold foil experiment is, as well as an explanation of the results of the gold foil experiment. This is a topic in both the SPM and IGCSE physics syllabus. There's of course a lot more to know about this topic, so if you'd like to find out more, please feel free to do your own research or watch my other educational videos. What I'll be covering in this video is just the general information that you would need in order to answer the questions in your examinations. So let's get started first with the history of the development of the atomic model. Now, I know this is science and it's not really history, but why we need to learn this is because we need to appreciate the effort and the hard work that physicists and scientists and researchers have put in to be able to contribute to our overall knowledge. Now, you should have learned about this history in chemistry or lower secondary science, but I'm just going to go through it in general very quickly. Now, about the atom. John Dalton came up with the first documented idea about what the atom is. He suggested that the atom is the smallest existing particle and cannot be divided further. That was his suggestion. Now, of course, this was disproved by J.J. Thomson, who discovered the electron. So he found that there were negatively charged particles, which he called electrons, and because there is an existence of negatively charged particles, obviously there will be a positively charged particle somewhere. So his idea of the atom is the entire atom is actually a positively charged sphere and the electrons are scattered randomly over its surface, just like a plum pudding. So why plum pudding? Because if you're going to make pudding with plums, which is probably something they ate a lot back then, so when you make the pudding and you have plums, you scatter the plums randomly throughout the pudding. That's the idea he had for his atomic model. So the atom is actually a positively charged sphere and the electrons are scattered randomly, just like how plums are scattered randomly in the pudding. And that's why this is known as the plum pudding model. Later, Ernest Rutherford discovered the existence of the nucleus inside the atom. Based on his discovery, the atom is not a positively charged sphere, but rather the positively charged particles of the atoms are focused in a really small section of the atom, and around it there's a lot of empty space and the electrons are scattered randomly in that space around the atom. Very shortly after, Niels Bohr discovered that the electrons are actually orbiting in shells outside the nucleus. And this is the model that most of you should have learned in your chemistry syllabus. So we tend to use Bohr's atomic model as our reference. Now, there are other models that were developed after Bohr's model, like Schrödinger. He suggested that electrons do not exist in shells, but rather exist in clouds around the nucleus. However, we normally learn this model because it's an easier model to refer to, especially to understand how chemical reactions work. Now, we're going to look at the gold foil experiment next, but just to let you know, we're going to be focusing on Ernest Rutherford's discovery. Why? Although his model is not the latest model, but his model was extremely important because he was the one who discovered the existence of the nucleus, and that's why it's known as the nuclear model. So the gold foil experiment proved the existence of the nucleus, and we're going to see how the experiment has done just that. Now, the gold foil experiment is also known as the Geiger-Marsden experiment. Who are Geiger and Marsden? Geiger and Marsden are two research assistants who worked with Ernest Rutherford. This experiment was developed by the two research assistants. That's why the experiment is named after them. Of course, the model was developed under the guidance of Rutherford. That's why this is Rutherford's model. So his assistants, Geiger and Marsden, constructed the experiment that led to this discovery. Let's look at what's going on in the gold foil experiment. Right? So on the left here, we have the lead block with a radioactive source inside. Now, if you haven't learned about radioactivity, you can still understand the gold foil experiment, but generally it's like this. So radioactive sources, they will release radioactive radiation in all directions, But in order to control the direction of the radiation, we encase it inside a lead block. And as you can see, there's a small hole here to direct the radiation to move only in one particular direction. This radiation is made up of alpha particles. Now, if you have no idea what alpha particles is, just think of it as they're positively charged particles for now. Now, to find out more about alpha particles, please watch my video on nuclear emission, where I explain not only alpha, but beta and gamma radiation as well. For now, let's focus on this. So the alpha particles are positively charged particles. I'm going to indicate that here. These particles are directed towards a piece of gold foil, and a fluorescent screen is placed in a circle around it. So the purpose is to try to detect the radioactive radiation of alpha particles. The purpose of the fluorescent screen is to try to detect the alpha particles, because alpha cannot be seen and it's not easy to detect unless you have something like the fluorescent screen. So first of all, when they did this experiment, they didn't put a gold foil in there. Without the gold foil, they directed the radiation, and they found that all of the radiation is detected on this side in a straight line. So none were detected on the other parts of the fluorescent screen. That means that the radiation of alpha particles travel in a straight line only. Then, when they put the gold foil, and it's a very, very thin piece of gold foil, they got some interesting results. They found that they get a very high reading directly on the other side, which means that the alpha particles were able to travel through the gold foil instead of being stopped by the gold foil. Not only are alpha particles detected here, there were also alpha particles detected on the rest of the fluorescent screen. So on this side, in front of the gold foil, but at the sides, they got quite a low reading. So they exist, but very, very low. Most of it here, a low reading on this side. So not only was alpha detected here on the fluorescent screen, they also found alpha detected behind the gold foil, but at a much, much lower rate. Very little, almost negligible, but the fact that they're there does not mean you can ignore it completely. So they found most of the alpha particles went through to the other side. So I'll put here high reading. So even though numbers may not be seen, but I want you to understand the high reading here refers to a very high concentration of alpha detected directly across. And in front at the edges here, low reading or very low instances, while behind, extremely low. So from these results, they found that, okay, this is a very curious set of results. And they needed to find a conclusion that could explain the results that they get. So remember, that's science. You don't twist the data to fit the hypothesis. You come up with a hypothesis to explain the data. And in the end, after much thought, this was the result that they came up with. So to explain the gold foil, what I'm going to do here is I'm just going to do a quick sketch of the gold foil 2D style. So let's say we're looking at this from the side. Say this is the very thin piece of gold foil. Now, it has to be extremely thin because we're trying to get the gold foil to be 1 atom thick. Now, whether that's possible or not, that's the aim. So I'm going to draw on the side here to kind of show you at an atomic level what's happening. So let's say these yellow circles are representing the gold atoms. Now the alpha particle, which I'll do in red here, is being shot towards the gold foil. Now remember, before Rutherford's model, it was Thomson's model. And if Thomson's model was true, if the atoms are all quite big, spherical in shape, by right, the alpha particles should not be able to travel through at all. It should have been blocked. But that's not true. As we found from the gold foil experiment, most of the alpha is able to go straight through to the other side. So if it could go straight through, that means there's actually a lot of empty space. So most of them were able to pass through. I'll put here a high reading. What this tells us is that there is a lot of empty space. So alpha particles able to pass through. This means there is plenty of empty space. So I'm going to put here a lot of empty space. Because if there was no empty space, there is no way the alpha could pass through. It would be stopped. But no, it's able to pass through. So this is an important consideration. Now, what else? We also found that some of the alpha particles, after going through the gold foil, changed direction. They were deflected. So the term deflected here means to change direction. So although the readings may not be high, and it could be very low, but it's still a significant thing to happen. Something has caused some of the alpha particles to deflect. Not only deflect, even though the reading is extremely low, some of the alpha particles went backwards. Again, although, slow reading should be negligible. No, something has caused a tiny amount of the alpha particles to reflect backwards. So we have to find out what's causing the deflection and the reflection. So the best answer they came up with was this. They knew that alpha particles have a positive charge. So what caused the reflection must be something that has made it repel. So something that's positively charged has made it repel. So the conclusion they came up with is that the positively charged part of the atom is not the entire sphere, but is focused in a small area within the atom. And that's what they call the nucleus. I'm representing the nucleus here with green circles. So the nucleus takes up a tiny portion of the atom. That's why there's so much empty space, allowing most of the alpha particles to be able to travel straight through. Now, because the nucleus is positively charged, this caused the changes in the direction. So some of the alpha particles may come quite close to the nucleus, and if they get close enough, they're going to get repelled. Positive and positive repel. So when it repel, they change direction, or if it hits straight on, it goes backwards. Now, the likelihood of the alpha particles to hit straight on is extremely low. That's why the reading for the backward motion is also extremely low. There's possibly a higher chance of the alpha particles to get close, and that's why this has a higher reading, although not by much, because again, not that many alpha particles would get that close to the tiny nucleus inside the atom of the gold foil. So this is the best explanation to explain the results that were obtained from the gold foil experiment. So I'm going to write it over here. So some alpha particles come close to the nucleus, and a few get reflected back. So what this proves is that most of the positively charged particles are focused in the center of the atom. So the nucleus is also where it carries most of the mass of the atom. So remember that back then, and even until now, we can't see the subatomic particles. We can't see the electrons or protons or neutrons. We can't actually see the nucleus. We're not able to see this and verify this visually that this is true. But how they were able to come up with the conclusion is based on coming up with an idea that could explain all the results in a correct scientific manner. And that's why the gold foil experiment is such an important contribution to understanding what's inside the atom. And that's it. So if you found this video educational and helpful, please click like and subscribe for more lessons, solutions, and exam strategies from your physics teacher, Miss Ho. Happy studying!